You may well have heard of the normal distribution before. You might have seen graphs that resemble this bell-shaped curve at the bottom, and you might have heard people talk about the tail end of a bell curve or some measurement that follows or fits a normal distribution. We're going to investigate exactly what that means, and we'll look at how we can use the normal distribution model to help us make sense of a whole range of different scenarios. Before we dive into that, I'd like you to look carefully at the picture on the left. Take a look at the weights, look at what you can see from it. I'd like you to ask yourself these two questions. What do you notice and what do you wonder? And I'd encourage you to pause the video at this point and write down anything you can to answer either of those two questions. Once you've done that, come back and I'm going to prompt you with a few more questions you might want to ask. So here's a few questions you might care to ask yourself. Why are some weights visibly more worn than others? If you look carefully, you'll see that the paint has been scraped off the weights, the point where you push the pin in. Why do you think this is? Why is there more wear and tear on some than others? Do you notice anything about the pattern or the distribution in general? What is the most commonly lifted weight on this machine? You may not know that for sure, but perhaps you can make an estimate based on what you can see in the picture. And similarly, could you estimate what proportion of users lift between 30 and 90 pounds? Or perhaps give the probability that the next user lifts a 100-pound weight. Now, I can't give you exact answers to these questions, but hopefully you can see from the picture that it might be possible to come up with a reasonable prediction based simply on the amount of wear and tear that we can see here. If people are pushing a pin into the weight that they plan to lift, then we can see straight away the most common weights people tend to lift. We're looking somewhere in the 50 to 60 pound range, perhaps around here. They seem to be the most commonly used because they're the ones that have been worn down the most. And by the same token, up here we have some that are only just slightly worn and others even further above that are barely worn at all. A 15 or 20 pound weight is unlikely to be used apparently. And similarly, any weights beyond about 100 pounds down at the bottom are also fairly uncommon. This ties in with what you can see on the bell curve at the bottom of the slide as well. There are some commonly used weights that perhaps lie within this range, and then there are some less commonly used weights, perhaps right at the tail end up here and at the tail end down here. And yet there seems to be a reasonable amount of symmetry in this particular picture as well. We're seeing that the number of people who lift more than 90 pounds is probably similar to the number of people who lift less than 30 pounds. You might make some kind of estimate about what proportions are involved. It's very hard to see exactly unless you know how to convert the amount of wear and tear into the number of times the pin has been pushed into a hole, but you can probably make a reasonable assumption that the probability of somebody lifting a 100-pound weight based on what we can see on this machine is probably fairly low. I'd say less than 5%, given how much and the frequency of use within the middle range and how much it tapers off towards the end. We're going to look at how we can use the normal distribution to model this more precisely, and then using only two key statistics, the mean and the standard deviation, we'll be able to answer questions like what proportion of users lift between 30 and 90 pounds, what's the probability that the next user lifts 100 pounds, and so on and so forth. So let's start by recapping what we mean by a statistical distribution. You've already come across a few. In fact, you've dealt with some since you first started learning about probability. The uniform distribution, as the name suggests, is a probability distribution where the probabilities are all the same, uniform as in all the same. So the classic example will be you roll a dice. You roll a fair six-sided die, and the result will come out looking something like this. You can make a table that represents all the possible outcomes. So that's what the small x tells you there. 1, 2, 3, 4, 5, or 6. That's what you could get. And then underneath, the probability that you actually get that particular score. So there's a 1 in 6 chance of getting a 1 when you roll that dice, and there's a 1 in 6 chance of getting a 2, and so on. This is what the graph would look like. Very boring. Every single bar on the bar graph is the same height, each of them coming out at about 16%. 1 in 6, if you want to be precise. This one is known as the uniform distribution, and if you want to find a formula that describes the probability for something like this, then you can. With a weighted dice, you might need to write down the probability for every single number, but for a uniform distribution like this, you can generalize. Say the probability that the score we get on the dice exactly matches any particular value is just 1 over n, where n is the total number of numbers on the dice. In this case, 1 over 6. So there's no need to perform a separate calculation to find the probability of getting a 4, or the probability of getting a 5, or the probability of getting a 2. They all give the same answer, in this case, 1 over 6. Here's a slightly different situation. Coin flipper. If you toss 4 coins and you count how many tails you get, then it turns out you don't get a uniform distribution. You might get no tails at all, 1 tail, 2 tails, 3 tails, or 4 tails. But some of those outcomes are more likely than others. The probability of getting 4 tails is 1 in 16 because you would need to get tails for the first coin, and there's only a 50% chance that happens, tails for the second, tails for the third, tails for the fourth. Each one is another 50% chance. So the probability of all 4 coming up tails is a half times a half times a half times a half. However, getting 3 tails and 1 head can happen in 4 different ways. Could happen like what we can see here, where the first coin that gets thrown comes out with heads, or it might be the second coin that gives you heads and the other 3 give tails, or perhaps the third or the fourth. That gives 4 different ways to get 3 tails and a head. And similarly, symmetrically, there are 4 ways to get 3 heads and a tail. And there are actually 6 different ways that you can get 2 of each. It could be the first and second, the first and third, the first and fourth, the second and third, the second and fourth, or the third and fourth. Now those numbers, 1, 4, 6, 4, 1, you might recognize from Pascal's triangle. They give us a nice little symmetrical graph again here, but you can see that the values near the middle tend to be more popular. So if you're betting on how many tails are going to come up, then you should be betting on 2 tails when you toss a coin 4 times. It's not just that on average it works out as half the number of coins, but it's more like there are lots more ways in which you can get 2 tails and 2 heads than there are ways in which you can get 3 of one and 1 of the other, or 4 of all the same. This one is known as the binomial distribution, which hopefully you remember. The binomial distribution also has a formula, but it looks a bit more complicated. So in this case, I've got n choose r times p to the r times 1 minus p to the power of n minus r. And the r is usually used in this case, but just for the record, x and r in this case would be the same. So you could replace r with x if you like, or you could write probability that x equals r equals n choose r, p to the r, 1 minus p to the n minus r. It essentially combines 3 different things. The probability of success a certain number of times, that's p to the power r. The probability of failure a certain number of times, that's the 1 minus p to the power of n minus r. However many coin tosses didn't come up tails, that's the number of times you need a failure to occur. And then the n choose r is the binomial coefficient. It's the number of different ways that particular outcome could happen. Now, both of these are examples of discrete random variables. They're called variables because the number varies. The number you get when you toss a dice could be anything from 1 to 6. So there's variability built into that. But also they vary randomly. So you can't predict what the dice throw is going to give you. And similarly, you can't predict how many tails you'll get if you toss 4 coins. However, the variables that vary randomly are discrete variables. That means there are only certain values that are possible. When you toss a coin 4 times and count the number of tails, you can only ever get 0, 1, 2, 3, or 4 tails. If you roll a 6-sided dice, there are only 6 possible outcomes, 1, 2, 3, 4, 5, or 6. What we're going to be looking at with the normal distribution is something called a continuous random variable, where instead of the possibilities being restricted to certain values, we'll have more like a sliding scale, or rather than a counting of something, like with the coin flipper, we might have the measurement of something. Just like when we look at the distinction between discrete data and continuous data. Notice here that the capital X, this is a little bit of a sneaky idea, but capital X is different to lowercase x in this context. The lowercase x is like a particular example of what you might get. So lowercase x could be 5. You might be saying, what's the probability that capital X equals 5? But the capital X itself is more like a representation of the experiment itself. If you are to roll a dice, what would you get? And there's no answer to that question. You can't say what would you get if you roll a dice, because the answer is, well, I don't know, it could be a 3. It might not be. It might be something else. But we want to be able to describe, if we can't say what capital X will be, we can at least say things about it. We can talk about the probability of it being a particular value. So one way that I find helpful to think of capital X is the outcome of the next experiment. If I'm going to carry out another experiment, if I'm going to toss a coin 4 times and count the number of tails, then capital X will represent in my head how many tails I am going to get. And of course, I don't know how many tails I'm going to get, but I can tell you with confidence that the probability that it's going to be 2 tails is 6 out of 16. So I could write the probability that capital X equals 2 equals 6 over 16. Or if I'm throwing a dice, I can say capital X represents the number that I'll see on the dice when I next throw it. And I don't know what that number is, but it could be one of 6 different possibilities. And I know the probability of it being any one of those things. Another way to think of it is representing the outcome of all possible experiments. So it's not something we can tie down and say it is this value or it is this value. But what we can do is talk about the probability of it taking a certain value. We can also generalize and say what's the probability that it's less than or equal to a certain number. If I toss a coin 50 times, what's the chance that I'll get between 40 and 20 tails, for instance? We can put bounds on it and talk about a range of possible values. And we'll do a similar thing when we get to the normal distribution in a moment. But it's important to remember that capital X doesn't represent some particular number that we just need to calculate. It's more like it represents the outcome of performing this random experiment again, and all we can say with any certainty about it is the probability of it taking certain values or being within a particular range. So the normal distribution is a way of modeling the behavior of a continuous random variable. Good example here would be the height of a person, or the length of a hamster, the weight of a randomly chosen newborn baby, or the speed of a randomly chosen horse. We're thinking of this in a sense like throwing a dice or tossing a coin a bunch of times. There is an element of randomness built into this, so that if you are to select a member from a population, then there should be something you can measure about that, and it's the measurement itself that we're interested in making probability statements about. This is a good way to start to make sense of the difference between continuous random variables and discrete random variables. So I want you to pause the video and have a think about this question. What is the probability that a randomly chosen person would be exactly 1.7 meters tall? Now, I'm not talking about approximately 1.7. I'm not saying to the nearest centimeter. I'm saying exactly 1.7. Have a think, pause the video. When you think you've got a number, an actual probability, then unpause and we'll see if we agree. Okay, the tricky thing here is that this is the kind of question that you would never really ask about somebody's height. We don't say who here is 15 years old, and then when someone says, oh yeah, I'm 15, you say, hold on a second, your birthday was 3 days ago. You're not 15, you're 15 years and 3 days old. When we talk about age, we're assuming that people are truncating their age. They don't quite round in the traditional way, but they will round down to the largest whole number that's no bigger than their age. But the chance of you meeting someone who has been alive for exactly 15 years, well, that seems pretty slim all of a sudden. You'd have to meet that person at exactly the moment, which is 15 years in the future from the moment they were born. It's the same with this. Exactly 1.7 meters tall? Well, basically zero. And it's not just roughly zero, it's exactly zero. The reason for that is that we're not dealing with a finite number of possibilities. We are dealing with an infinite number of possibilities. We're no longer saying how likely is it that you roll this particular number on a many-sided dice. We're saying how likely is it that your height is exactly 1.7 meters when it could have been any number within a range. Even if that range is fairly small, even if you could say that nobody is going to be taller than 2.5 meters and nobody's going to be shorter than 1 meter, even if you could say that, well, you've still got an infinite number of possibilities within that range. Even if you know that someone is between 1.6 and 1.8 meters, the chance of them being exactly 1.7 is still zero, because there's only one number that's exactly 1.7, and there's an infinite number of numbers within any given continuous range. So if the answer to the question is so nonsensical, then something is wrong with the question. Something about what we're asking doesn't make sense. We shouldn't be asking whether a person is exactly 1.7 meters tall, because it doesn't really make much sense to ask that question. What about, what is the probability that a random person is 1.7 meters tall to the nearest centimeter? And that's probably what you would naturally assume somebody means. If they say, are you 1.7 meters tall? Then you would assume there's some kind of range within which you would say, yes, close enough, we'll go with that. And in this case, that's equivalent to saying, what is the probability that your height falls within this continuous range between a lower bound of 1.695 and an upper bound of 1.705? And that's something you could actually put a number onto. It's worth thinking about this idea of probability of zero and the idea of something being impossible. Previously, you've been told, possibly even by an A-level maths teacher, I've told people in the past, I've taught this, that a probability of zero means something is impossible. And generally speaking, in the contexts in which we say that, it is true, but the context is often discrete random variables. We're talking about the probability of getting a 7 when you roll a 6-sided dice. There are no ways to get a 7, and there are 6 different possibilities. 0 out of 6, 0. And that is impossible. But there's a difference between that and, let's say, I pick a number between 0 and 1. Could be any number, 0.732249845, or whatever it might be. But it's a number that could be literally anything between 0 and 1. And then you have to guess that number. Well, now there's only one number that's the correct number, but there's an infinite number of possible numbers that could be my mystery number. So it's not quite the same as saying 0 out of something finite. We're now trying to find one correct value out of an infinite number of possible values. And that still kind of gives 0. There's no other number that we can put on that, but it's a different kind of 0 in a sense. It's the 0 you get when you try dividing by infinity. So it's a strange one, but it's not the same as something being impossible, because it is possible to be exactly 1.7 meters tall. It must be, because well, I'm taller than 1.7 meters. So, and at some point I was shorter than 1.7 meters. So somewhere in between, I must have been exactly 1.7 meters at least once in my life between those 2 points. So it happens, but I suppose you could argue it might happen for a brief instant of time, a moment in time when you happen to be exactly 1.7. And the likelihood of finding someone ever who's exactly any given height is still 0, even though people are particular heights at different times. It's a little bit of a strange one. So generally speaking, if we're dealing with continuous random variables, it doesn't make any sense to ask what's the probability that this equals something. The only way we get meaningful answers is if we ask questions involving a probability range. We could ask, how likely is it that this person is shorter than such and such? Or how likely is it that this person's height is between this and this? Incidentally, we can use the normal distribution calculation model that we're going to talk through shortly to estimate things like the probability of someone being roughly 1.7 meters tall. There's a 3% chance that an adult male will have a height that rounds to 1.7 meters, to the nearest centimeter. Incidentally, there's about a 5% chance that you'll be within half a centimeter of the mean height, which is 178 centimeters. This is based off data for adult males in the United States. So it may be slightly different depending on your population and gender. Now we're going to look at the mathematical basis behind the shape that we recognize as the normal distribution curve. It's also known as a bell curve because it looks vaguely like a bell, or the Gaussian distribution, named after the same mathematician Carl Gauss, who you might have come across when learning about arithmetic series. Now, the mathematical formula for this graph looks something like y equals e to the minus x squared, with a few graph transformations thrown in for good measure. Now, you'll be grateful to hear that you don't need to memorize this formula. No one's going to ask you what it is, but I think it's interesting briefly to look at it and think about what will happen for large or small values of x. So if x is equal to 0, you'll have e to the power of 0, which just gives a 1. So the height of the graph will be just 1 over root 2 pi times 1. But as x gets bigger and bigger, e to the minus x squared over 2 will get smaller and smaller. It's exponential decay. But if x is a negative number, when you square it, you still get a positive result. So it's still exponential decay even as x becomes more and more negative. And that's why this graph seems to tend down towards asymptotes at y equals 0, both for positive values of x and for negative values of x. The other really interesting thing about this, and the reason it's been scaled down in the way that it has, been stretched by scale factor 1 over root 2 pi in the y direction, if you like, is that this graph now has an area of 1 underneath it. Even though technically the curve goes on forever in both directions, it gets so close to the x-axis so quickly that just like with a geometric series that has a small enough common ratio, you can calculate the total area of this shape, which is technically of infinite width. Because the height gets small so quickly, the total area is 1. It never goes above 1. And that 1 is going to be really important for us because that is going to relate to the probability of certain events taking place. Essentially, the area under the curve tells you the probability that your continuous random variable will take certain values. And this ties in nicely with what we were saying about it being impossible to say what's the probability that our continuous random variable is equal to something. The area enclosed under the graph between, let's say, x equals 1 and x equals 1 is 0. There is no area if you've just got a single line. You have to have a range. You've got to go between two different values to get any kind of non-zero area at all. So if you've got a range of values, you could think about the lower bound and the upper bound for your two values, calculate the area in between, and hey presto, you've got the probability that your continuous random variable takes a value within that range. This is more commonly what the normal distribution curve will look like. Just by messing with the scaling on the x and y axes, you can make any normal distribution curve look like this. So this is generally what I will sketch when I'm in the middle of a normal distribution question. I draw a quick diagram here, and I mark on the key features so that I can check that my answers make sense. It's going to be particularly useful when we're looking at working backwards with a normal distribution curve, when you already know a probability and you're trying to work backwards to find the values. But we're going to start by doing the forwards direction, and we need to understand a few important features of the curve before we start calculating with it. The first thing you want to notice is that it is perfectly symmetrical. You can kind of see that from the mathematical formula, the fact that you've got an x squared in there we've talked about, but the curve is perfectly symmetrical, meaning it's exactly the same above the peak as it is below the peak. That means that the area to the left and the area to the right of that middle point, the highest point, they're exactly the same area. And since the total area is 1, the area on each side of the middle line must be 0.5. Now I'm writing them as percentages in here because they represent probabilities, so it's often helpful to think in terms of percentages. It helps us usually to have a slightly clearer intuitive sense of what's going on. There is also a point of inflection. This, mathematically speaking, point of inflection refers to the moment when the curve stops getting steeper and starts getting less steep, or maybe stops getting less steep and starts getting more steep. In this case, as you move along from the middle line, from the midpoint towards the right, you find that the curve starts out with a 0 gradient at the top, but then the gradient becomes more and more negative up until a certain point. And at that point, the gradient won't get any more negative. It's got as steeply negative as it's ever going to get. And at that point, it changes the direction of the gradient change, if you like. It's a bit of a subtle one. It's a more subtle point than a stationary point. We can see what stationary points look like. They're often maximum or minimum points, or they may be a stationary point of inflection, like the wiggle that you get in the middle of a y equals x cubed graph. But this is a non-stationary point of inflection. The curve stops being rounded up and over, if you like, and starts being rounded down and in. So the middle section of this graph curves in such a way because the gradient is decreasing throughout the middle. Whereas beyond that point of inflection, as you move to the right, the gradient is now increasing again. So it starts at 0, and as you move along, maybe it gets as steep as, I don't know, on this diagram with this scale, kind of looks like it's got to a steepness of maybe -2. But then the steepness starts to increase again from -2, maybe -1.5, -1, -0.5, approaching 0 again as the curve moves to the right. That point of inflection is where the gradient changes from decreasing to increasing. And there's another one on this side. The gradient is increasing up to the point of inflection, and then it starts to decrease after the point of inflection there. The mean is the center of this distribution. For a perfectly symmetrical distribution, the mean and the median are the same place. But the key statistic that we use when we're dealing with the normal distribution is the mean itself. We give it the value mu, and it sits right in the middle here. Not only that, but we can identify those points of inflection that we talked about by using the standard deviation. The mean plus the standard deviation gives us this point on the curve where the curve starts to change its gradient change. It's the moment when the gradient stops increasing and starts decreasing, or vice versa. It's a change in concavity is another way to call that. And if you split further, you can see that the 50% that we had above the mean can be broken into a couple of chunks. There's a 34-ish% chunk between the mean and the mean plus the standard deviation, and then the remaining 16-ish%, it's more like 15.7, but roughly speaking, this is a good rule of thumb. 16% lies more than one standard deviation above the mean, and there'll be an equivalent 16% that lies more than one standard deviation below the mean. So, for instance, if you have a mean score on an assessment of 100 marks and the standard deviation is 20 marks, you would expect 16 people to get at least 120. 16% of people, and you'd expect 16% of people to get a score as low as or below 80. And you'd expect the other 68% of people to get somewhere between 80 and 120. That's how this works. And if you have a continuous random variable that can be modeled by a normal distribution, if you know the mean and you know the standard deviation, then you can say with a high degree of confidence what proportions you would expect to lie in different sections. We've also mentioned how the curve is asymptotic. So as you move further and further from the mean, either above or below, the probability of being within any given range will shrink smaller and smaller. So that although theoretically you could go as far as you like, in reality you end up getting numbers that are so close to 0% that it's incredibly unlikely that you would ever get an example where this actually happens. Be like saying, what's the probability of finding a hamster that weighs more than a kilogram? It's very, very unlikely, because maybe the average weight of a hamster is 100 grams or something. And although the standard deviation might be 20 grams, 30 grams, you're not going to get very many standard deviations away from the mean before the probability of being in a position like that drops so low that it's never actually going to happen in practice. Here's a few key points that are worth remembering. They're good rule of thumb. The most important one is already demonstrated for you up there on the diagram, this 68% within one standard deviation of the mean idea. But more simply than that, the first thing that you want to get your head around is that 50% of the values lie above the mean and 50% lie below the mean. Remember, 0% of them lie exactly on the mean, because it's an exactly something. The probability of being exactly anything is 0, but the probability of being above the mean is 50% and below 50%, which is equivalent to saying the mean and the median are the same. Roughly speaking, 68% of values lie within one standard deviation of the mean. So if you know the average height of people and you know the standard deviation of people's heights, then you could confidently state that about 68% of people are within a particular range, whatever the mean is, give or take the standard deviation. If you go further afield, if you jump to 2 standard deviations above and 2 standard deviations below the mean, you're now encompassing about 95% of the population. So somewhere in between those two, somewhere between 1 standard deviation and 2 standard deviations, is where you would find the quartiles. You remember that the, before 1 standard deviation, the upper and lower quartiles contain the middle 50% of the data, which means it's going to be something like 0.7 standard deviations above and 0.7 standard deviations below the mean. That would correspond to the upper quartile and the lower quartile, so that you've got 25% above and 25% below at each end. But you can see that we've got 68% within 1 standard deviation, which is pretty much 2/3 of the population, increasing to 95% within 2 standard deviations. So you're casting your net a bit further afield now and saying, well, we're going to be more flexible. We're going to allow values that are surprisingly high and values that are surprisingly low, but still not so high and so low that you'd be gobsmacked to discover something outside that range. In fact, within a class of 20 students, you would expect that nearly all of them would lie within 2 standard deviations of the mean for whatever it was you happen to be measuring, but you'd probably find that one of them was either surprisingly tall or surprisingly short compared to the average, or maybe they are surprisingly good at holding their breath or surprisingly bad at holding their breath. Whatever it was you were measuring that was modeled by a normal distribution, you'd find that 5% of the values fall outside this range. But if you spread your net even further to within 3 standard deviations of the mean, then you're going to pick up all but 0.3% of the population. So yes, there will still be that handful who are at the extreme end, one way or the other. I once shared a cabin with a chap who was 6'8", which is definitely at the tail end of that distribution for height. You will meet people who are particularly tall or particularly short or particularly good at solving IQ problems and particularly poor at solving IQ problems. Whatever it might be, there'll be people at each end of the spectrum, but within that 3 standard deviation range, you'll find 99.7% of the population. We can move this curve around by changing the mean. Basically, that means if you think about the normal distribution curve on a set of axes, you can translate it horizontally, and you can also stretch it or squash it by changing the standard deviation. In fact, when you change the standard deviation, it both stretches it horizontally but also squashes it vertically to preserve the property that the area underneath will be exactly 1. So that's always going to be preserved, but it means you can basically have a normal distribution curve that fits your own specific situation. It doesn't have to have a mean of 0 and a standard deviation of 1 like the picture at the top. We can modify it to get the standard deviation, the normal distribution that fits the mean and the standard deviation for our own particular situation. Now we need to look at some data and decide for ourselves if we think it might fit a normal distribution, given what we know about the properties of a normal distribution. So in this case, I'd like you to pause and have a look carefully at the graph that you've been shown. We've got the heights of 10,000 people marked on a histogram. I'd like you to think about what makes it look like it might be a good fit for a normal distribution, and then look to see if you can find any reasons why it might not be a good fit for a normal distribution. Pause the video and try to write down an answer to both of those questions, and then continue watching and we'll see what we can figure out. So initially, the first thing I would look for is whether or not we get that symmetrical curve. A normal distribution is symmetrical, and this graph certainly looks pretty symmetrical. The other thing is the asymptotic behavior. So there's definitely higher values in the middle, and then it tails off pretty precipitately as you move further and further up to one end or down towards the other end. So you're not finding very many people who are as tall as 200 centimeters, and you're not finding many who are shorter than 140. Most people seem to be somewhere in between, somewhere around the average of maybe 168 on this particular graph. So all of those are good reasons to model this with a normal distribution. But there's something that doesn't quite match. Apart from the more subtle things you might investigate, like is it true to say that 16% of the values are 1 standard deviation above the mean or more, there's a more important thing that we can pick out just by looking at the diagram. And that's that little dip in the middle. Something not quite sitting right with that dip. This is a distribution that we would describe as a bimodal distribution. There's not just a peak in the middle, there appear to be, if you look closely, 2 different peaks. There's popular heights just to the right of 170, maybe 174, 175, and then there's popular heights just to the left at maybe 164, 165. So it might well be that what we're looking at is 2 different populations, each of which individually maybe fit a good normal distribution curve. But if you try combining them, that does not necessarily give you something that a normal distribution will match nicely. In reality, that exact same data you can see on the curve on the left, having been split into male and female, and drawing both of their histograms together, you can see where the discrepancy comes from. In fact, these do very closely match a normal distribution, each of them separately, but combined, they don't. The average height of the men in this particular data set was about 175, and the average height for the women was just a little over 160. Somewhere in between, there were few enough men who were short as 170 and few enough women who were as tall as 170 that the 170 mark, somewhere around there, gave the lowest value on the aggregate combined distribution graph. So it's worth looking carefully and seeing if you can identify things like that. It's a bit of a subtle one in this case, so if you spotted it, well done. But we're looking for evidence of symmetry, and we're looking for evidence of a single popular region. So we're not looking for this double peak. We're trying to avoid that. We would be suspicious if there was a skewed distribution where there was one tail longer than another, and we should be suspicious if we see a bimodal distribution. Next, we're going to work through an example together. So we'll start by thinking about the weight of 6-month-old baby girls follows a normal distribution. We are given the mean weight and we're given the standard deviation. As an example, here's a 6-month-old baby girl that I made myself earlier. A random sample of 1,000 babies is taken from the population. And we would like to first sketch the distribution of baby weights, and then how many babies from this 1,000 should we expect will weigh more than 8 kilograms, how many would weigh less than 5.6, and then how many are likely to weigh between 4.8 and 9.6 kilograms. So to begin with, this sketch, even if you're not asked to make a sketch, is often a really useful first step with any question involving the normal distribution. And we can bear in mind these key figures. You may not have all of them committed to memory, but they're useful ones to have in your head if you can, particularly the first couple. You want to make sure you know about those because they're really helpful for interpreting and sense checking your numbers. Make sure that they are reasonable. So when we sketch the distribution, we start by just drawing a normal distribution curve, try to make it look symmetrical. And then the key information we're going to add on there. Notice we've got a mean of 7.2 and a standard deviation of 0.8. And I've encoded that information in this particular way. X and then a little wobbly line. N stands for normal distribution. And then we've got the 7.2 and we've got the 0.8 in there, but in a slightly strange way. 7.2, that seems fine, so we've got the mean. And then instead of writing 0.8, I've got 0.8 squared. Now you might remember from your previous statistics that if you square the standard deviation, what you get is the variance. So in general, if we write a number, comma, and then another number, what we're referring to is the mean and the variance. When you start using your calculator to do questions involving the normal distribution, it will just ask you for the mean and the standard deviation. But if you're looking in a textbook and you see X is normally distributed and we're using n, open brackets, 5, 16, close brackets, then what you're dealing with is a mean of 5 and a variance of 16. So you need to square root it and get an answer of 4 to actually find the standard deviation that you want to use. It's basically because variance turns out to be a useful measure for all sorts of things. So variance tends to be used as the sort of default in here, although it may seem a little bit strange. Still, once you've got those values, you can start marking them on your diagram. The 7.2 is the first one to go on. That's the mean that goes in the middle. Then there are two other values that it's really useful to include. There may be more depending on the question, but in this case, the most useful additional values, as they will often be, are the points which are 1 standard deviation above and 1 standard deviation below the mean. So I've got 8, which is 7.2 add 0.8, and we've got 6.4 kilograms, which is 7.2 minus 0.8. Those are the 2 points that correspond to the points of inflection on the curve, so we can see from the shape of the curve where those numbers should go. But also, we know from the details given at the bottom of the page roughly what proportions I would expect to lie between those two values or either side. In particular, we should expect about 16% of our 1,000 babies to weigh more than 8 kilograms because 8 kilograms is that cutoff that is 1 standard deviation above the mean. Less than 5.6 kilograms? Well, 5.6 kilograms is 2 standard deviations below the mean. And because 95% of the data lies within 2 standard deviations of the mean, that means the other 5% is outside that range. And because of the symmetry of the graph, 2.5% will be more than 2 standard deviations above the mean, and the other 2.5% will be more than 2 standard deviations below the mean. So I'm expecting 2.5% of the babies to weigh less than 5.6 kilograms, and that comes out as 25. The last one, between 4.8 and 9.6. This is quite a wide margin. Some of those babies weigh twice as much as some of the other ones, but that should cover pretty much the entire visible curve that you can see in my diagram. And because those numbers work out to be 3 standard deviations above and 3 standard deviations below the mean, respectively, we know that that corresponds to 99.7% of the population. All but 3 babies will lie within that range. And even in a sample of 1,000 babies, you would only expect a tiny handful to be either bigger than 9.6 kilograms or smaller than 4.8. Now you should be able to have a go at a few questions from exercise 3A. I recommend 1, 2, 3, 5, and 9. Now we're going to look at how we can make use of the fact that the area under the curve is exactly 1 and see how we can estimate some probabilities directly from the diagram. Then I'm going to show you how to use the Casio ClassWiz to calculate those probabilities more precisely. So to start with, we've got a representation of the continuous random variable, the height of a randomly chosen adult male. They have a mean height of 178. That we can see from here, and the variance is 8 squared, which means the standard deviation is 8 centimeters. So we would expect, roughly speaking, for the peak of this distribution to be at 178, and that's certainly what it looks like. And then if we move 8 to the right or 8 to the left, then we'll find those points of inflection. What I'd like you to try is use the fact that the area underneath this curve is exactly equal to 1, which in this case, with this scale, means that every single large square you see in front of you is 0.05 or 5% probability. See if you can answer the following 3 questions. Estimate the probability that a randomly selected adult male is taller than 190 or shorter than 178, or between 170 and 186. Have a go at those using the diagram. Think about which region of the diagram you need the area of, and then come up with an approximation, an estimate for the area. Don't spend too long trying to get it precise, but see if you can come up with a reasonable value, or at the very least a range of values within which you're happy the answer lies. When you've got values, unpause the video and we'll check to see how close you are. Okay, so the first one is everything above 190. Taller than 190 means the area within this tail. Now, if you look carefully at, say, the first section between 190 and 195, that's the biggest part. And that looks like about 5% to me, because although it's not a complete square, what it misses off the square more or less is compensated by the extra bit it has at the beginning. So roughly speaking, I'm going to call that bit 5%, or perhaps a little bit under. But then the remaining sections, this part looks like a little less than half a square, and then there's a few other bits as we go along. So probably overall more than 5%, but less than 10%. Now what you get if you do it precisely, and I'll show you how to do that shortly, is 6.68. So if your estimate was close to that, then well done, you've got a good eye for this sort of thing. Shorter than 178. Now 178 hopefully has jumped out at you because that is the mean itself. So if you are wondering what the probability is of being shorter than 178, it is going to be not just approximately, but exactly 50%. And that's because 178 is the mean and the curve is symmetrical, so you'll have the same area to the left as you do to the right. And the last one here, between 170 and 186. Well, 170 is exactly 8 below the mean, and 186 is 8 above the mean. So these are the values that correspond to the points of inflection on the curve. They'll be roughly there and there. And if you want the area between the two, then that's one of our standard results that we saw before. Just like 50% of the values will be below the mean, we also know that about 68% of values will be between one standard deviation below and one standard deviation above the mean. If you get a precise answer, it comes out at 68.27% to 2 decimal places. But if you remembered 68%, then fantastic. If you went with something like 2/3, that's also pretty good. Now, I'm going to explain how we can calculate those precisely and talk through how we can answer these questions at the same time. To do this, you're going to need your Casio ClassWiz calculator. And if you go to menu option 7, called Statistical Distributions, it's got a picture of the normal distribution curve. In fact, on the menu, so you should be able to find it pretty easily. You'll see these 7 options. The first screen before you scroll down will give you the top 4: normal PD, normal CD, inverse normal, and binomial PD. And then the next 3 will give you binomial CD, Poisson PD, and Poisson CD. Now there are some of these that you will not need to use, so it's worth being aware at this point. You won't need the Poisson distribution. That's for measuring something a bit different. It's another discrete distribution like binomial, but you won't need to make use of it. Binomial PD and CD you both use PD, or probability distribution, or probability density. That one gives you the probability of a particular value being equal to something. So the chance of your discrete random variable being the same as a certain number, whereas CD, the cumulative distribution, gives you the probability that you'll get less than or equal to a certain number of values. There's a similar thing going on with normal PD and normal CD, but as we said before, it doesn't really make sense to ask the question, what is the probability that someone is exactly 1.7 meters tall? So normal PD doesn't quite do that. It's more like giving you the idea of the probability density, or how essentially how tall the curve is at a particular point. And it's not something you ever need to use, so you can stop worrying about that one straight away. Because every question we have within a normal distribution calculation will involve a probability of a value being within a range, the main one we're going to be interested in here is normal CD. And we will later look at the normal inverse to see how we can work backwards. But normal CD is what we're going to be using for all of these ones. Now, if we want to calculate something, this is the best way to do it. When you go into normal CD, you want to think about first the mean at the very bottom and the standard deviation, which comes just above it. Those are the numbers that you can pull out from the definition you're given at the beginning. Just be careful. This one wants the standard deviation, not the variance. And then you define a lower and an upper bound. So I've given extra details just underneath here so you can see what it would look like in practice. We're saying how likely is it that my continuous random variable, lies between, say, 167.5 and 168.5. In other words, what's the chance of somebody being 168 centimeters tall to the nearest centimeter? And this will calculate that probability for you. The good thing about this is that you can have an upper and a lower bound of whatever you like, and you just put the numbers in, it'll calculate it directly. For question 1 here, for instance, between 176 and 178 centimeters tall, you just type in 176 for the lower bound, and you type in 178 as the upper bound, and the answer will jump out for you, 9.87%. So pretty high chance, because that's a range of values which is reasonably wide. It's a 2 centimeter range, and it's very close to the mean. In fact, the top end of it is the mean itself. So just about 10% of people you meet will be either the average height or 2 centimeters below, or somewhere in between. Between 100 and 178. This one's an interesting one to try, because 100 centimeters is way off the charts. If we look at the graph we've got, it shrinks down towards practically 0 by the time we get down to 150 centimeters. If we try going any lower than that, we're not going to find much of any interest. We can put those numbers in, but the calculator tells us the answer is pretty much exactly 50%. The calculator cannot tell the difference between this probability and the probability that we found over here in question B, shorter than 178, somehow gives the same answer as between 100 and 178. This is going to be useful for us, because you'll notice the way the calculator works, it doesn't let you put in just a lower bound or just an upper bound. You have to put in both. But we can fool it a little bit by giving it a lower bound that is so low that it's indistinguishable from no lower bound at all. It'll be a bit like me saying, what's the chance of you meeting someone who is taller than 6'7"? and me saying, what's the chance of you meeting someone who is between 6'7" and 20 feet tall? Well, the answers to those questions are going to be the same, even though the questions are subtly different, because the second question, which gave you an upper bound of 20 feet, doesn't really exclude anybody. There aren't any people who are taller than 20 feet tall, so you don't need to worry about that affecting your answer to the question, what's the probability? We can make use of that fact when we answer questions like question 3. Less than 170? Well, that means there's an upper bound of 170. If we give it a ludicrously low lower bound, in this case I'm going for 100 again because that seemed to work fine for the last one, then certainly to 2 decimal places of accuracy, and in fact in many cases to significantly more, this will be ample for giving you an answer which is equivalent to the probability of being less than 170 centimeters tall. So you make up a lower bound if there isn't one already, but you make one up that is a long way below the mean. By a long way, I mean in the context of your standard deviation. A long way from the mean might be 8 centimeters, it might be 50 centimeters, it might be 0.2 centimeters, depending on your standard deviation. Roughly speaking, if you're 4 or 5 standard deviations beyond the mean, then the probabilities associated with those regions are going to be so small as to make no difference at all. If in doubt, just go with a number that seems ludicrously far away, and you'll be fine. Similar for the next one, more than 2 meters. Well, we now have our lower bound of 200 centimeters, but we don't have an upper bound, so we make one up. I'm just going to put a number in of 500, and that will work just fine. In this case, we get 0.3%, so only 3 people out of every 1,000 are likely to be more than 2 meters tall. And then the last one, we need to come up with the upper and lower bound, but it's going to be similar to what we've got in the example at the top here. 178 to the nearest centimeter is going to be somewhere between 177.5 and 178.5. And that works out as pretty much 5%. Remember, although it's quite a narrow range, it's only a 1 centimeter range, it's that narrow range that is the most popular 1 centimeter range. If you had to guess how tall someone will be to the nearest centimeter, then your best bet is 178, because that's the mean. And 5% of people will have a height that rounds to 178 centimeters to the nearest centimeter. And although that may not seem like a very large probability, it's a larger probability than any other 1 centimeter range. You might hear a similar statistic in terms of how likely it is that a baby will be born on their due date. And although the probability is relatively low, it's still a greater probability that the baby will be born on their due date than that they will be born on any other individual day. So if you're having a sweepstake, then you still go with the due date. It's the most likely, even though it's not that likely. It's more likely than any other individual result. Just one other quick point to make. When we see a phrase like between, it can be a bit ambiguous. When I say between 10 and 20 items in this box, does that mean you're allowed 10, or does it need to be more than 10? Are you allowed 20, or is it less than 20? Luckily for us, when it comes to the normal distribution, we don't care about those distinctions. Less than or equal to, more than or equal to. They're all the same, and they're all the same because the probability of it being equal to anything is 0. So you can use whichever of those you like. You can use them interchangeably. If you've written or equal to along with your less than sign, then that's not going to make a difference, and it doesn't matter whether you do or you don't. Finally, this last question I'm going to show you involves more than one statistical distribution. It's going to use a little bit of the normal distribution initially, as we can see, but also as we get into the question, it's not just the standard normal distribution that we're working with at the beginning, but the second part of the question talks about a multi-pack with 12 packets of crisps. We want to know whether or not it contains more than one underweight packet. That reminds me of binomial distribution, because we've got a fixed number of trials. Getting a packet of crisps and weighing it will be a trial effectively, and then a fixed probability of success. Part A is asking you to find the probability that a packet is underweight. And part B is asking you a question about how many packets might be underweight. So for part A, we're going to start by identifying the mean and the standard deviation. Remember, 3 squared is the variance, so 3 is the standard deviation. Then we write down the probability statement. Find the probability of a packet weighing less than 28 grams. We just write that using this notation. The weight W is less than 28. Then we need to make up a lower bound, because we need this to be in the form lower bound is less than weight is less than upper bound. And in order to make this work, I've just gone with a ludicrously low lower bound. It's a long way below the mean of 34. So we should be just fine. It's more than 10 standard deviations away from the mean. So it's going to be indistinguishable for the calculator from the probability of W being less than 28. Then you go to the normal CD mode on your calculator, as we've done all the way through here. You put in your lower bound, your upper bound, sigma and mu, and we get a probability. 0.0227 something. So rounded to 3 significant figures, we get 2.28%. That seems reasonable, and we can check that it's reasonable by noticing that 28 grams is actually 6 grams below the mean, and the standard deviation is 3. So we are 2 standard deviations below the mean. And if we're 2 standard deviations below the mean, then that means we're down to the tail end, where roughly speaking you'd expect about 2.5% in that tail end, because about 95% of the values will lie within 2 standard deviations of the mean. Now for the second part, we need to define our variables, and we're not using W anymore because we need to count the number of underweight packets. The probability that we have more than one underweight packet means we're now definitely dealing with a discrete distribution. So we define X to be the number of underweight packets, and this is what our binomial distribution will look like. There are 12 trials, and each trial has a 2.28% chance of being successful. A successful trial in this context means an underweight packet. So we're counting the number of underweight packets, therefore a packet being underweight is what counts as a success. And we're asking the question, how likely is it that we have more than one? So we write the probability that X is more than 1. That is our probability statement. But in order to turn it into something we can calculate, we need it to be in the same format that the binomial CD mode requires, which means it should have a less than or equal to 1. Now it's worth noticing here that if you get in a muddle, you can write down what numbers are included. What is the chance of X being bigger than 1? Well, that means it could be 2, or 3, or 4, and so on. What about less than or equal to 1? Well, it could be 1, or it could be 0. And then you can see that that kind of covers all your options. 2, 3, 4, 5, 6, 7, 8, 10, 11, 12. They're all the options that are at least 1. Sorry, greater than 1. And then all the options that are no greater than 1, or less than or equal to 1, that's everything else. That's 1 and that's 0. So we know for sure that because they cover all the options, the probabilities add up to 1. And we can find the chance of having more than 1 by subtracting the chance of having 1 or fewer. The same as if you said that person has more than 1 car. That is the exact opposite of the statement that person has 1 or fewer cars. Because if I say he has more than 1 car and you say no he doesn't, then you would have to justify that by telling me how many cars he has, and the only valid answers would be he doesn't have any cars at all, or he just has the 1. So we use binomial CD, we put our numbers in, and remember the probability we're getting here, this isn't the chance of getting more than 1 underweight packet, this is the probability that X is less than or equal to 1. So we then need to remember to subtract it from 1 to get the final result, 2.95%. And as you would expect, it's a pretty small number. The manufacturers will be expecting potentially some of their multi-packs will come out with more than 1 underweight packet, but they're also banking on the fact that most people are not going to mind if 1 or 2 packets are underweight, especially if the majority of packets are overweight. They're going to get more than the number of crisps that they've been advertised for anyway. And if they do complain, well, there'll be a small enough proportion of people complaining that you can factor in the additional cost. You can send them a £5 voucher and they'll feel very happy all over again. You now should be able to try a few questions from exercise 3B, practicing using the normal CD calculator, and in some cases using additional knowledge from binomial, I would recommend you try questions 5, 6, 7, and 8, and then questions 10 and 12, getting a little more complicated and involved towards the end.